What if we were secretly doing math this whole time? I'm Ray Myers. Welcome to Craft versus Cruft. And today we have an extra special guest to close out the year of formal methods. Renowned teacher and some would say formal methods expert, Hillel Wayne. Hello, you may know that you were actually, along with Marianne Bellotti, one of my biggest inspirations to do the year of formal methods, as well as simply the year of generative AI producing so much uncertainty that I was compelled to search for any source of certainty I can. Can you let me know how you got started down the path of formal methods? Like why this has appealed to you so much?
Certainly. First of all, it's fantastic to hear that I was inspiration for you to do this whole year of formal methods. As you know, I put a lot of time and energy and love into trying to make this stuff more accessible to people, and to know that it has these kinds of effects is just really gratifying to hear.
Yeah.
So I actually got my start as a web developer. I was working on an education platform for elementary schools, and we had what I like to call an accidentally distributed system between what we were doing and the vendors we were working with, and then the school's infrastructure, and then Apple's multiple device management systems. We had a distributed system. We would have partial outages, we would have race conditions, we would have all sorts of very unusual bugs that people say only happen with at Google or Amazon scales. But we were 15 engineers. Many systems become distributed systems very quickly. And we were looking for tools to make this a bit more dealable, to make it easier for us to find and fix these bugs. I at one point stumbled on formal methods and applied to the systems. It solved some really, really hairy bugs for us. I've just been a huge fan of it ever since.
Now, I've tried to explain to people what formal methods is because it's many different things, actually. We've talked in some recent episodes about formal verification, but there's also modeling and specification. And so these all kind of operate under this umbrella. In your own words, what do you think is just a high-level summary of overall what we're trying to do with it as a pursuit, and what some of the specific flavors of it are?
Formal methods is a very broad field that collects a lot of different subdisciplines. It's almost more defined by this philosophical goal than necessarily specific technique goals. And that philosophical goal is to write provably valid software. But there are many ways we can approach writing provably valid software. There's the formal verification of code, where we actually take our code and we take our theorems about the code, and we show those theorems match the code. You can also go one level higher. You can be talking about the designs you're going to be coding up and figure out if there's bugs in pseudocode or systems that will become code. That's sort of the level I work at. It has some pros and cons versus the more direct code verification. And this is colloquially called formal specification. That's technically a bit of a misnomer because formal specification matters on all sides. But if you say you use formal specification, people will usually assume you're doing the kind of work I'm doing, if they have a sense of the differences.
So I think the most common reaction when I mention formal specification, which I've had a chance to actually try in a professional context a few times now, and just been really impressed with the results. It's non-obvious that I would so quickly be able to get any value out of it.
Yeah.
Because people say well, just because the spec is right, and then, the code might not match the spec. Code notoriously has bugs in it. So why would we be shifting our focus to the design doc when so much of our experience has taught us that, the code doesn't match the documentation anyway?
That's one of the big challenges of sort of, as you found, advocating this stuff. Code doesn't match the documentation. And it does remind me of one of the first cases where I've seen formal methods used. It was at that first company I was working at, where we had planned out a system to solve a problem. And we basically quickly scribbled out a design, and we're going to code it up. It was estimated that it would take me about a week to code up this really scribbled design. And before we started, though, I was like, let's take a moment to try to specify this out. And we took a moment to write a specification for it, mostly to sort of practice specification, not necessarily because we thought it would be that necessarily it would find issues. And then after we specified, we're like, okay, we're going to run a model checker on this design to find out what it says this design can do. And then we look at it and it spits out saying, okay, if A, B, and C happens, you might have this bug. And we look at the code that we plan to write and we're like, okay, so what does happen if A, B, and C happens? Had to redo the entire design. Turns out to be an unfixable flaw in the code. And yeah, it turns out that yes, you can have bugs if your code doesn't match the design. But if your code matches the design, it better be a good design, right? And it's much better to have a bug because your code didn't match a good design than that your code perfectly matched a terrible design.
Yeah, we've all seen such code. So there's this feedback cycle, like I'm from the extreme programming community, kind of disciplined implementation of technical practices that support Agile.
Right.
So the thing that is often said is, certainly if you're going to have documentation, you should be doing it incrementally, but you want to be getting feedback as early as you can. Now, I've now taken that value, like kind of counterintuitively, I wound up where actually I really like kind of starting, at least find some aspect of a design doc that I would like to model and just see what comes out of it as a way of getting that early feedback. There's kind of a complex feedback process when you talk about like, okay, specifying the design, doing the implementation, that feeds back into something you might need to change about the spec and the design and so on and so forth. Do you have any kind of stories from what the evolution of specifications are over time? Because, we know that you don't just implement code one time. Like you will have to change the spec later. Has that been difficult?
Not necessarily. So first of all, I really do like how you put it that extreme programming is all about getting feedback as fast as possible. And having to write a bunch of code to get feedback on your design is very slow. So you might as well get faster feedback by writing formal methods. I do like that. I might have to use that in like some of my writing. I do really enjoy that way of presenting it.
I read it between the lines on your blog. His blog is great, by the way. You should check that out.
Yeah, HillelWayne.com. I'm currently on hiatus because I'm writing a book, but it'll be back soon. So the idea is like, how do we sort of reconcile this fact that like as code's changing, the design changes, right? There's a few ways we can approach that, but I think the main way is to work at a high enough level so that code changes don't necessarily reflect fundamental design changes. One good example of that is imagine you're trying to communicate between two servers, right? And you're writing code on that. And the code might be like, okay, we have to have a retry mechanism, right? We have to talk about like how we're going to log it. We might have to change the code because we have to change the API is slightly different. You can imagine a lot of ways that you might have to change the code revolving around connecting two servers to each other, right? But like at a high design level, fundamentally, your logic boils down to this. Talk to the server. Does it succeed? It succeeds or it fails. If it fails, we retry some amount. Maybe we stop retrying. And that basically ends up being like 4 or 5 lines of specification, depending on the language you're using, of course. And what that boils down to then in the end is that as you change the code, you change the design, but the changes to the design end up being much smaller than the large-scale changes to the code. That said, it does still require discipline, does still require a lot of work. And this is one of the things that does limit people's adoption of these tools. I'm not going to pretend these tools are perfect. Anybody who doesn't use them doesn't have legitimate reasons not to be using them.
Let's talk a little bit about the difficulty.
Yeah.
Because, and some of these have been a little easier to get into.
Which ones have you found the easiest, if you don't mind me asking?
Once you convinced me, to really give it a try, TLA Plus, I was able to at least get through the tutorials pretty well. Leslie Lamport's video tutorials are very good. And actually, I did find it relatively easy to, at least get something going. Also, Z3, I because I've done Lisp before, the parentheses didn't scare me on the SMTP lib syntax. There's also the Python one, but I actually prefer writing in the Lispy syntax. And so Z3 I found pretty easy to do, although it's very low level. But Z3 is incredibly powerful in terms of its flexibility.
It's almost like a machine code.
Yeah. And Dafny as a programming language, if you're looking for if you're a functional or imperative programmer that's looking to mix in a little bit of this, Dafny I found to be a very accessible language. Then when I got in the deep end of the pool, I'm liking Lean Prover the most. That's for me, this is the deep end of the pool, like an actual theorem prover, actually doing tactic proofs. And then it's also a pretty versatile functional language. Still makes my head hurt, but those are
it makes all of our heads hurt.
Those are the main tools I've been using.
Let me ask you. I'll ask you a reflective question. What is your favorite programming language?
Yeah. It's not production ready yet, but I think Rocklang by Richard Feldman has got the most of the right idea. And then so probably by extension Gleam.
Okay. These are both good picks. And Rocklang is actually great because, if I recall correctly, Rocklang was based on Richard Feldman's work with functional programming and Elm, right? Because he used to be part of the Elm core team. Elm was heavily inspired by Haskell, right? Haskell was strongly influenced by Miranda, Hope, and metalanguage. Metalanguages came out of the same disciplines that I believe in the same area was a lot of the work on Algol. Algol was influenced by people's influence with Fortran. Fortran was based on hardware abstraction over vacuum tube computers.
All right.
Okay, so you see that there's this huge chain going backwards of people learning off like programming languages. Here's the chain for Lean. Lean, Isabelle, MetaMath. When we talk about modern programming languages, we're talking about these things that have been built on like 6 or 7 or 8 generations of people learning and innovating off languages towards like new languages, finding the ways that these fail, making improvements to them, exploring new ideas. With formal methods, a lot of the formal methods were in generation like 2 or 3. It's just not nearly as developed in terms of like all the hard lessons being incorporated into new ideas as we've seen in like in the broader programming world.
So I think that something I really like about Elm and Rock now, right, is that it's got the things I like about Haskell, but Haskell was unapologetically a research language. You know, it was cutting edge. I think a lot of these, you know, easier to use advanced functional features you see in even mainstream languages now wouldn't have happened as fast or as well without Haskell, but Haskell did not do it the easiest, right? Like, and so now we have like kind of a friendlier version. There's been a distillation from that, and that we haven't seen maybe with theorem provers yet. Like if Lean was the Haskell, like what's going to be the Rocklang for a prover language, if it's even possible?
Yeah, I mean, every theorem prover is partially a research project and partially like a work project. I think Lean's one of the first that has like really strong industry backing too. All the other theorem provers have historically come out of universities for work in like researching mathematics and have been later adapted towards doing software work. Could be wrong about the history, but I think that's the broad path.
I think that general pattern is right. So you proved left pad, or specifically, you led a large effort to prove left pad in as many provers as possible. Why do we want to prove a function as simple as left pad?
Maybe we don't. Maybe left pad is so obvious that we don't have any bugs, except for the time that one person did submit a left pad to this thing that they did not prove correctly and did have a bug. But generally, left pad came out mostly because of a couple reasons. One, I was leading this challenge to basically show that functional programming wasn't necessarily better for proving than certain branches of imperative programming. This was back in 2018 when I was like younger and much more brash about these things. And one of the things we discovered as part of that like Twitter project was that left pad is actually a really interesting proof target because it is both really obvious what it does, but has some subtle properties that are kind of can be tricky to prove, but not so tricky you need to pull out lots of really specialized machinery. So it is just difficult enough that it's a great showcase of how different languages in theorem proving approach proving. And that's why we end up using it. Now, generally the reason why you'd want to actually prove it in a real system is because, it's so simple and so obvious you want to prove it. But then something else is going to use left pad, and that's going to probably be a bit more complicated. And that's also going to be used by something else that's more complicated. And it's going to go 5 chains down. You don't just call left pad, you call it as part of a function that calls a function that calls a function that calls a function. And if you want to make sure that top level function is like working correctly, you need to make sure all the foundations are working correctly too.
It sounds like you're saying there's common core code that is like much more high impact than code we might casually write. Although like I think the trajectory will continue to happen that we can get higher and higher assurances of more and more of our code if we use the best available techniques, but it's kind of a slow burn. Critically core libraries or, infrastructure like a compiler, for instance, right? This is where I think a lot of people see this is high leverage in the sense that bugs affect a lot of other software. So this shifts, would you say, the economics of it being worth investing in a formal methods technique?
I'd say off the top of my head, the most of the time when I think about like code that's been formally verified to use in industry, it usually involves the HTTP stack. So I believe Project Everest out of Microsoft and Iron Fleet also out of Microsoft and a few other approaches are really focused on getting like internet connections working properly and internet protocols, because if those go wrong, you can have like malicious code execution. There's also some interesting stuff with SMT solvers, especially about authentication control. I believe Amazon, they've been doing a lot of stuff with like using SMT solvers to show that a resource control policy gives the certain kinds of access we want or do not want.
There's a new thing Amazon's doing with SMT solvers like every other week. I've seen so many neat articles by them and different techniques. The last one I saw was like using full, I think, formal verification on like, the Dafny implementation for one of their auth things. Usually they're doing kind of a hybrid approach, I think, where they are proving a formal specification that's maybe even a runnable reference implementation, but not like not efficient enough one. And then they'll go in Rust or some other industrial language, implement the spec, and then they'll even use like sometimes fuzz testing to try and achieve assurance that the reference version matches the production version. This is really interesting to me because the sort of advanced architectural trade-offs of how are we going to, leverage our different techniques to give different kinds of assurance. Do you know of any like particular architectures you think have become go-to?
It's definitely early enough in like sort of the formal methods like development that it's not necessarily clear what's going to be like the winners. There's some sort of things that we've been seeing more of. Common thing that you do see is like the idea of like a verified core, and then everything outside that core is tested less rigorously. Like just because something isn't formally verified doesn't mean it's bad. It just means that less effort has gone into making sure it's correct. And often that's the correct trade-off. Like the difference between 99% assurance and 99.999% assurance is enormous sometimes. So it doesn't make sense to do this kind of thing where you focus on only the highest profile thing. What we're also seeing a lot of is the idea of using a specification, like a high-level system design, to generate tests. So not using it to verify code, but using it to test code, which is a very subtly slightly different thing. TLA Plus just added some features to make this easier. I'm going to write about that soon. Yeah.
So actually, while you're mentioning TLA Plus, I had an Alloy question for you. TLA Plus and Alloy are two of the modeling tools that you've spent a lot of time writing about. Though what I love about your blog is you survey the whole space a whole lot. Like you're obviously very curious about it. You're not just like, I wrote a book on TLA Plus, so I'm going to just talk about that now. But I heard from you, that Alloy in a relatively recent version added temporal logic.
Yeah. And
so now your models in Alloy can be temporal in nature. And this was a big spot of you would have to use TLA Plus for it now. But so that's really cool. But now my whole intuition of when I should be learning one or the other has been reset. So how do I know? Because I usually am talking about a temporal dynamic. The models, I care about the behavior that changes over time. Now maybe I should use Alloy for it. Is there, an example of a way I can make the decision between Alloy and TLA Plus now?
It's always so complicated. I mean, and there's also like other tools out there like P, there's MCRL2. I'm going to be spending a lot of my courses just trying to study MCRL2. It's a very fascinating one for a very specific reason. I don't know, like how do you tell a person whether they're supposed to use like Zig or Rust or Hair or like, it's always so challenging to find like, here's the exact reason you should use one or the other. But at the same time, I feel like saying, just try both and see what you like better isn't really helpful, right? The question was Alloy or TLA Plus. And I'm going to say like, I've explored both a lot. It's still not necessarily clear to me when I start which one I'm going to use. There's a few like heuristics I have. One's going to be better than the other. Like if I have to do multiplication, TLA Plus can do multiplication. Alloy kind of struggles at it. If I want visualizations, Alloy has really good visualization tools. TLA Plus does not. Both languages are changing regularly, and sometimes something that's like good for one over the other can flip. So it's always a bit challenging to sort of say like, definitely learn one or the other. I think at this moment, there's more better free resources for learning TLA Plus because it has more industry momentum, but that doesn't mean you should write off Alloy entirely.
So I wonder how your thoughts about formal methods and its relationship to practical software development. Have you thought about how the landscape has changed with how many people believe that AI will change the face of software development? Like, do you see a relationship between these different pieces?
AI just isn't that good at formal methods right now. It just does not, there's not enough information out there and not enough samples of language for like LLMs to do a good job with them. At the same time, though, I don't want to write them off entirely because LLMs have been enormously useful in my own coding. I use them quite often. They are fantastic tools. I like to kind of describe them as like a genie that can only give you crappy tools you want, but any crappy tool you can imagine. And it turns out that like when you can imagine any crappy tool you want, you get some amazing stuff. You just have to like know how to use it properly. I mean, I hear people say like, oh yeah, it'll create more focus on like people creating high level designs and the AI will just fill them in. But I don't know that. Nobody knows that. Nobody knows how this is going to turn out. 3 years ago, nobody had any idea that AI would be this crazy. Maybe we're going to hit the ceiling like next year. We don't know this. Maybe it's going to be that AIs just take over everything. Like I feel like we're in this situation where like we don't know the future and we're so uncertain about what it could be that we're just trying to come up with guesses of how it's going to revolutionize stuff. 10 years ago, somebody asked me what I saw as the future of programming languages, and I'm like, the only thing I can predict is that there's going to be a language that's really popular in 10 years that we haven't heard of now. That's the only thing I can predict.
So I think as we're closing out here, I think something that I've tried to do on this channel this year is provide just some like inspiration of like this is some really powerful concepts and tools. And yeah, you will have to kind of explore if you're willing to take that journey. I found so much rewarding there. Just sort of to that end, you know, I wonder if you have any parting messages.
I guess what's been inspiring me is seeing that I've been seeing more people actually using it. Like it's one thing to talk about like how useful these tools are, but I think we all know that like there's the difference between the actual like people talk about how amazing they are and people actually using them. And to see that people are using them and are being successful with them is what inspires me, that this has been worth all of the love and all the attention that we've all been putting into it. That's my answer.
Awesome. Well, thank you so much for making the time. It was not, you've got holiday travel, and thank you for making the time to do this interview. Let us know, tell us about your book and where we can find you online, and we'll wrap up.
Right. So I'm working on a new book right now called Logic for Programmers, available on leanpub.com/logic. And what it does is it covers the ways that formal logic is very, very powerful in software engineering. It covers things like property testing. It covers decision tables. It covers database constraint analysis, formal methods in planner programming, constraint solving, and a bunch of other topics, showing how each one is augmented or sometimes made possible entirely through the use of mathematical logic. I also have a website, hillelwayne.com, and a blog at buttondown.com/hillelwayne. Those are the best places to find me online.
Yeah, and I've really enjoyed a lot of that material. So until next time, thanks again for joining us. And as Lao Tzu said in the Tao Te Ching, with patience, the most tangled cord may be undone.